Buenas tardes a todos. La próxima presentación, que será dada en inglés también, cuyo título es Application and Impact of Coupled Fracture and Reservoir Modeling. Va a ser presentada por Garret Fowler, que trabaja en Reservoir. Adelante, Garret. Please, Garret, your turn.
Good afternoon. Are you able to hear me?
Yes.
Okay, fantastic. You never know with these web conferences. But thank you very much for the introduction and the invite to speak here this afternoon. I'm going to cover some of our experience as a company building and tuning coupled fracture and reservoir models and the value of various diagnostic sets of data that operators are collecting with more and more frequency over the last couple of years. So as we progress through the presentation today, I think any presentation with modeling needs to start with why we do modeling, what is the value of doing physics-based modeling. And then I'll briefly introduce a few of the more common diagnostic data acquisition sets that operators are acquiring in fields today. And then discuss how we incorporate those diagnostics into history matching and tuning numerical models. And then finally end with the application of those models. Similar to our prior presenter, the end goal of these modeling efforts is not just to build a model that matches historical data, but in fact take that model and use it in a forward sense to somehow make a better decision or improve the economics of your development. So first, what is the value of numerical modeling? Why do we do it? And we often get pushback from people who say kind of the common verbiage is garbage in, garbage out, right? So there's no use in building a model unless you have really great calibrated data. And so that's one of the things I want to show today is that even with a fairly sparse data set, we can make pretty impactful changes and insights with numerical modeling. And that's because models are physics calculators and demonstrate the logical consequences of the assumptions that we put into the model. So there is a set of equations that the model must obey. And if we put in our assumption of permeability or porosity or saturation or compressibility, we then see the consequence of that assumption. And while we may not be able to dial into the exact parameter with a 1% uncertainty, we can discard data that we can clearly evaluate as erroneous. And beyond that, models support the scientific process. So they allow us to make a hypothesis and test that hypothesis and then assess that versus real data or another assumption and see how that varies. And again, gain a collective understanding of how different parameters play with each other. And then I might challenge our prior presenter, but I think we're in agreement, just using different language, in that I don't claim that subsurface models are digital twins, and I don't think they can be because there will always be uncertainty. And that's maybe in contrast to the beginning of this session, where we had a presenter talking about surface-based models. And there, I believe we can create digital twins, exact replicas in a digital environment of offshore structures or pipeline networks. But that level of fidelity doesn't exist in the subsurface. And so our prior presenter handled that through an ensemble approach, and I think that's a very wise way of doing it. And we can also gain insights on kind of the portfolio of representative parameters by using diagnostics to hone in on what we think a reasonable breadth of those parameters is. So as a demonstration, here is a model, or the modeling technology we used. This is the ResFrac simulator that my company builds. This is a 5-well model, multiple stages across each of the wells in an unconventional environment. So what we're going to do in a single model is fracture 2 of the parent wells, which are the 2 interior wells, produce those for 4.5–5 years, and then frac the offsetting 3 wells in a wine rack pattern and produce all 5 wells together. And so what we'll see is the interplay and the coupled nature of simulating both hydraulic fracture propagation and production in a single model. And so that's really the differentiator, is by coupling these processes. And now we're going to go into production. We'll see pressure drawn down, and then here come the children wells being fracked together as well. And so in modeling this in a fully coupled nature, we can see that interplay of fracturing and reservoir production effects. So at the beginning, I introduced the objective today is to really talk about how we can incorporate these various diagnostics into the model building process and calibrate. And in doing so, I separate these diagnostics into 2 categories: direct measurements, where the data that we're extracting from the diagnostic is directly measuring that effect. So an example of this would be the cross-well fiber optics, where when we measure the strain response of a fracture crossing an offsetting well, that is a direct observation. We're directly measuring the strain in the fiber optic gauge. Another example would be optical imaging. If you put a camera down the lateral and image the perforations, that is a direct measurement of the perforation diameter. However, generally direct diagnostics are more limited in terms of feasibility and availability, and we often rely on indirect, which are also valuable. So things like diagnostic fracture injection tests, where we're measuring pressure versus time, and from that we infer things like stress and permeability and pore pressure. Similarly, with microseismic, what we measure is a failure in the rock that creates an acoustic signal, and from there we interpret things like fracture geometries. So as an example of incorporating 2 different kind of levels of diagnostic data, I'm first going to pull from an SPE paper that we wrote with Recoil Resources last year, or I think actually early this year at LACPEC. And this is an example of an indirect diagnostic data set. So we had very few direct measurements, but instead relied on indirect measurements to history match and tune the models. And so this was a 2-well pad in the oil window of the Eagleford. We had standard petrophysical logs that gave us things like porosity and permeability after our interpretation. And so that's an example of an indirect measurement. Similarly, perforation efficiency through step rate testing. That's, again, interpreting a pressure and rate signal to assume or to measure perforation efficiency as indirect. And then microseismic to measure fracture geometries. And so we were able to build a model and history match. You'll notice that there are gaps in between fractures here, indicative of the measured about 60 to 75% perforation efficiency. And so one of the ways that we looked at the data was also in an RTA sense. And so in this paper that we wrote, we walked through kind of these steps of interpreting RTA data, and are able to do so to assess which model parameters we think are more representative of the subsurface. So what I'm showing on the left-hand side is the cumulative oil versus time. The dashed green trend that I'm highlighting with my mouse is the actual data. And there are two wells, but they only had one measurement point, and so they assume both wells are producing the same. And then we have two models that reasonably match the data. The models I'm calling the A and the B model. And so B is in purple, A is in orange. And we see that both of the two lines for each of the models represent the two wells in the model. And so you can see they straddle, in both cases, straddle that historical data set. And so the question is, should we use model A or model B? And looking at the RTA plot in this sense helps us narrow that in a little bit, because now we've taken that rate and pressure data and actually transformed it and looked at it in a different way. And so here we can see that the purple B model matches that RTA data much better, and particularly in this late time slope of the trend here is equal, whereas this orange slope is actually lower or less than the slope of the green actual data. And so the implications there on, say, 30-year predictions is greater than like 20%. So the production difference of the two models would be meaningful if assessing something like well spacing or cluster spacing, or doing some sort of sensitivity analysis with these models. So maybe in contrast, I'll then bring an example of a very heavily diagnosed science pad. So this was a tight gas shale. We had microseismic, which we used to corroborate fiber optics that they had in offsetting wells, a DFIT to calibrate permeability and stress, but then we had these direct measurements. So they had optical imaging of the perforations before and after the stimulation to measure erosion and how much the casing has eroded, as well as the cross-well fiber optics. And so this is where you have a fiber optic cable and an offsetting well, and are able to actually measure the strain response as fractures cross. And so that's really where I wanted to focus today, is just show some of the statistics and ability to match this cross-well data. So here's a model of a single well, and I've put in this observation well in the lower image that you can't see in the upper images here. But we're modeling 3 stages along the lateral, and you can see the treating plots here of those 3 stages. And then in the lower right, what I'm showing is the stress profile that's evolving through time. And what we're going to do is use that to measure various statistics of this observation well and compare that to the actual data. So zooming in here, and I'll play a video, what we're going to watch is how this stress state evolves over the treatment. So here's the first stage treating, and we can see that tensile failure in front of the frac tip, and then compressive forces on the side. And we're seeing the same thing on the second stage and the third stage. So then the question is, how do you use this data in a model? Well, this is the model. What do you compare this to calibrate a model? And so the data set that you would get from an offsetting well is something like these waterfall plots that show the strain response over time, or this displacement over time in this case, as you progress through time. And so here's that you'd have the tensile blue tip in front of a fracture, and then followed by this compressive on either side as the fracture crosses that observation point. And so from this data set, we look at not only when a fracture hit occurred, but how many fractures are crossing per stage, what's the location, is there a heel bias or toe bias, what is the propagation rate, so we know when we began pumping and we have the measurement time. So what's the minimum crossing time of a fracture, maximum, what's the average crossing time. We can even see things like fractures reopening or post shut-in propagation. And so we're going to use all of that from the data set to tune our numerical model. So for instance, here in the model, we can look at exactly what time that first fracture crosses, when the second fracture crosses, what the difference is, if a fracture doesn't cross before shut-in. But then what we see here is post-shut-in propagation. So on the left-hand side, here's stage 1 that has completed. This fracture just adjacent to the white box has not yet crossed our observation well, and we've begun to frack stage 2. When we're fracking stage 2, we can actually see propagation of that same fracture after that stage 1 has completed. And so we're able to replicate the same effects that we're seeing in the microseismic or fiber data in a numerical model. And then we get things like the second stage crossing and so on and so forth as you move down the wellbore. We can see additional things like a fracture that doesn't quite cross, but you can see this yellow region right in front of the fracture tip that we may actually be able to see on the observation well as well. So in doing so, we can very finely tune both overall fracture length and geometries, but also the rate of propagation, which helps us tune things like rock toughness and the propensity to reactivate fractures if there's evidence of fracture reactivation. Say if you have multiple wells where you're fracking over adjacent well bores, you may reactivate existing fractures that were previously stimulated. All of that can be taken from this cross-well fiber optic data and imparted into a numerical model. So again, returning to how do we use these models, they're physics calculators. We can test hypotheses. So an example would be, you think that more limited entry might improve production. Well, you can increase the limited entry in the model, run the simulation, and then assess, did it actually improve production? And importantly, then answer why. So that's an example of that first data set that was published in the prior SPE paper. Remember, originally we had that 60 to 70% perforation efficiency across these wells, as indicated by these blank gaps across the lateral. We were able to iterate on design, keeping fluid and proppant volumes the same, but increasing limited entry. And you see the shorter fractures as that same fluid is distributed across more clusters and more active. And as a result, we actually get a higher perforation efficiency and more production. So have a second case study here showing the impact of azimuth, which is also a function of permeability, whether or not these clusters are going to interfere, and then being able to replicate that in a data set, which we did with the direct measurements and looking at why or why not. You are seeing evidence of interference and the change in azimuth when they change drilling directions here. So when you drill off azimuth, you can see SH max here is horizontal across the flood. The cluster spacing between these two simulations is the same, but the effective fracture spacing is smaller when you're drilled off azimuth. And so that then has implications on cluster spacing and optimal well design. So in summary, numerical modeling is a valuable tool in scientific process. We can test hypotheses, we can compare those. Direct observations provide very robust, concrete data that we're measuring explicitly at a point in time. But indirect measurements are also still useful, like microseismic and DFID and step rate testing. There is just more of an uncertainty band around those measurements. Those diagnostics reduce uncertainty in the model and help us calibrate. And then those models improve the insights and are able to be utilized in a optimization sense to improve the economics and returns to the operator. And as a company, we're continuing to progress our understanding of these diagnostics and how to incorporate them and the learnings on history matching. And in particular, we're leading a joint industry study next year modeling parent-child interactions using that coupled reservoir and fracture simulator that I showed and used for the examples in this study. So this is an area of active research, and we're pretty excited about where these diagnostics are evolving and the utility that is coming to numerical modeling.
Great presentation, you'll be on time. I have the first question. What frequency of diagnostic is recommended?
Sure.
That's the first part. And the second part is, this second question is for Jesus Ochoa from, I believe, in Argentina. He said, great presentation also. Have you applied this methodology or compared this model to data in Argentina, Vaca Muerta?
Yes, I'll answer the second question first. So,
okay.
Yes, we have 2 active clients in Argentina, both of which are modeling Vaca Muerta. So we have been able to history match and validate the models in Argentina in the Vaca Muerta. For the first question, the frequency of acquiring these diagnostics, I think the best model that I have seen for operators to employ is using very heavily diagnosed science pads. So choose a well pad in which you want to obtain all the scientific data that you can, and we can talk about how to rank those various diagnostics, because obviously budgets are limited. But then what we've found is that once you calibrate a model to a particular area, it's fairly extensible. And the examples I'd use of this are, we've done quite a few blind tests in the Permian, where we'll calibrate a model to a very large diagnostic data set, and then test the model on a different diagnostic data set a mile or 5 miles away as a blind test, and see whether it can replicate the same diagnostics and measurements. And we've had a tremendous amount of success doing so. And so I would say, as long as you're within a basin of like rock, you can calibrate to a single point and make it extensible. What would not be appropriate would be, say, like calibrating to the Bakken and then trying to apply that to the Vaca Muerta. They're different rocks and they behave differently, and you need to calibrate in each location.
I have another question for Santiago Cerverisky. For the case of cross fiber optics, did you show a comparison between model and measurement? If so, would you mind recapping it? He might be missing it.
So I didn't show it a direct comparison, but and the reason for that is it hasn't been published yet. So I'm showing an example of the example water flood plot, and then I showed stress here. But in the ResFrac simulator, you can also output a waterfall plot to compare directly, and that work is going to be published at ATCE. Going to be published at HFTC in February with Apache. So Apache in the Permian did an extensive project with crosswell fiber optics. They actually had 2 crosswell monitored wells in a 12-well pad, and we were able to model and replicate all of those diagnostics, and that's going to be published at HFTC in February.
Okay. I have the last question that you have only 1 minute to answer. Do you have an example where natural fracture are first detected by seismic and then correlated to result of these models? A way to differentiate the induced fracture from the natural ones. Correlation of the area with other completions.
Yes, that unfortunately not a question I think I can answer in 1 minute, but that's a very important piece of data that we would incorporate into the models. Things like image logs as well give us an indication of natural fractures. In terms of representing those in a model, I might direct you on our website, the resfrac.com website. We have a series of free videos that we post up on the website, and there's about an hour-and-a-half long talk that Mark McClure, our CEO and founder, gave for ARMA last year on the difference and evidence for complex versus planar fracture models. And it's about a 90-minute discussion that actually addresses that question in particular.
Yes, I can imagine that. Well, thank you very much. It was a very good presentation. A lot of comments here that maybe you can see later, and maybe you can answer to the other people. Thank you very much.